Welcome to Displaced Gamers. My name is Chris and this is Talkin Code episode 4. In the most recent episode in the Behind the Code series, we focused on Mega Man 2, environmental collision detection using forward collision checks and zipping. I wanted to talk about code performance by doing a code walk and count CPU cycles along the way. We'll get into some math in this episode and also get into Mega Man 3 performance and improvements as a bonus at the end of the video. If you've not seen the Mega Man 2 Behind the Code video I mentioned, you may want to watch that first, as I will casually reference several of the subroutines that were named in that episode. We've got a lot to cover. So let's start first with walking the Mega Man is standing section of that Mega Man handler and look at how long it takes for move Mega Man horizontally to execute. And we're going to use the Heatman stage. We're going to use this room from the Heatman stage, which has those blocks that are appearing and disappearing because they're on a timer. So let's freeze this at a certain point. I'm going to enable the debugger now. Hopefully you can see this. This is the entire debugger window for Messin. And there's a lot to take in here. You probably want to see it on a large monitor. And yes, we're going to walk a lot of code. So grab a taco, your favorite beverage. We're going to do a code walk. So starting where we are right now, we've just hit our breakpoint at the jump to Mega Man is standing. So the first thing we're going to do is jump forward to there. There are two RTS, let me move this down a little bit. Two RTS areas here and here. The one that I usually see the return happen from the Mega Man is standing section is the one that's down here. But the main area that I want to focus on is the move Mega Man horizontally sub, which we walked in the Behind the Code video for Mega Man 2. If I execute the code and move all the way down to our call, I want us to make note of what the cycle count is here right now, because that's going to be our starting count before we jump into move Mega Man horizontally. We're going to walk all that code, and when we come out of move Mega Man horizontally, we'll take a look at that cycle count and we'll subtract the two values and see how many cycles it took to execute this one call for this one frame for the move Mega Man horizontally subroutine. Now more stuff happens in there than simply moving Mega Man horizontally, and we covered some of that in Behind the Code, but I'll briefly kind of touch on it as we move through it. So if we enter the subroutine, you can see that I have a few notes here for what gets loaded into 2D, 2E, and 2F. I'm going to move through this a little faster than usual, than I usually narrate each and every line, so I'm going to rely on the comments quite a bit in order to get us through it. So the first thing, we initialize 0, which is going to be used for, I think, one of our returns that's coming up soon. The direction that we check to see if Mega Man is facing, he's currently facing left, so we want to use that in order to know to move Mega Man left instead of right, so we skip ahead to left. This value, this bookend value, whenever you have a lot of consecutive rooms together that lets you scroll from left to right, for example, the left room might be room 2, and then you walk through 3 and 4 and 5, and so you have a left room bookend of 2 and a right room bookend of 5. And that's basically how it keeps track of how many rooms you can move through before, hey, it's time to move vertically, etc. So we move through here. In fact, we're in a room right now that doesn't really scroll. So we go ahead and move forward to move Mega Man left continued. That's just what I call it. Hey, SEC. We're a little bit more familiar with SEC and CLC prior to doing some sort of calculation. This is going to be a subtraction. So apply horizontal velocity to Mega Man. We do a subtraction here because we are moving left. So our X values are going to decrease if we have a velocity. We do the fractional value first. And at this point, if we manage to move left and go under 0 as we're subtracting, the carry bit is going to serve as a borrow, and hey, that's going to influence our integer value. Right now, Mega Man is just standing. There is no value to subtract here. Page kind of deals with our rooms. Naturally, if we move backward from room 3 into room 2, we want to influence that. Again, we're just standing. Nothing's going to happen here. So then next we have what his X position is, and look at that, 8. You know what that means from the previous video. We're checking the front of Mega Man. He's facing left, so we take his X position, subtract 8 pixels, and we store it in RAM value 08. This is a parameter that's going to be used as part of our Mega Man check forward collision sub, which is just underneath. One parameter I didn't talk about that we also pass into this function or subroutine is the current page location. And if the front of Mega Man is on the next page, then you want to make sure that we've set the page value properly, and that's put inside of RAM location 09. Now we're ready to go into the check forward collision sub. So this is the main subroutine that we talked about quite a bit inside the last Behind the Code video. There are 3 locations to check. So to start the loop, it takes our current index, clears the carry flag, and it basically looks up the distance that we're going to get for the current thing that we're checking. And we work this loop backwards, so we're starting with the feet. So it looks up the current value, it sees B, which is decimal 11, and it basically adds it to Mega Man's Y position, stores it in 0A, which is our parameter for the dynamic level environment collision check sub, which is coming up in a bit. I named this F9 screen wrap flag, and I haven't fully investigated it. I just noticed that, hey, this value does change whenever we screen wrap front vertically. There might be more behind that than simply a screen wrap, but that's just what I happen to call it in RAM. And so it figures that screen wrap in just in case the current page that we're on is going to change based on where we are on the screen. So we set that parameter in 0B, and we call the dynamic level environment collision check sub. So now the interesting thing about this call is we're in the Heatman stage, and there are blocks that are appearing and disappearing. And I think at the moment there are actually 3, and one is either fading out or fading in. And you see that we have, well, heck, look at it right now. Dynamic environment object array size at RAM location 55, the value is 3. This value in RAM is used to basically hold how many dynamic level environment objects that we have right now. And we do have 3. We have 3 blocks. You could be in another room and this value would be 0. And basically that helps us from having to loop every single possible object slot. If you can have, say, I don't know, 8 objects on the screen at the same time, you don't want to have to loop every single one of those. If you're putting an object into index 1 and then, oh, this one went into 4 and this one went into 2, well, now you have to loop the entire thing every single time, even if you only have 3 objects or if you have 0 objects. And so this keeps track of how many dynamic objects are currently on the screen at once, so it knows to check the minimum amount of objects. Now we have blocks in here at the moment, so we are going to enter the checking loop. Basically, we have our dynamic array right up next to our object array size 55. We start 56. So we have 56, 57, 58, and they hold the offsets to get us to the proper places in the 600s. So it puts that offset into X, and then we use it through here. Now, Mega Man is not currently involved in or close to any of these blocks, but we still have to go through them. All right, so now we've arrived at level environment collision check sub because we didn't find any collision in the dynamic level environment collision check sub. And the first thing it does is it loads the current level into A and it ANDs it with 07. And the whole reason it does this is because this code that we're in right now, which you'll see is in the C1000 hex block. Remember when we talked about bank switching and how we have a 16K bank followed by a second 16K bank, and you can actually see them at the bottom of the screen. I may need to make this larger so you can see it. So the 8000 address in ROM is currently set to 0E. That's the bank that we're looking at. And the C1000 is 0F. And the 0F is locked, and the 0E is the bank that we switch. This is using Mega Man 2 is using an MMC1 chip. We're currently in E, and we need to bank switch to the appropriate bank for our current level because we need to look at the patterns, look at the tiles that make up the current level. This code that we're looking at right now is common code that's going to be used by every level. But as soon as we start examining the specifics of, in this case, the Heatman level, we need to switch to that bank. And the value for Heatman is apparently 0. So if we go into the bank switch subroutine, if you recall, it takes 5 writes to, in this case, FFF0 in order to switch the bank. And if I walk this code and get all the way down to the last bank switch, which I haven't executed yet, if you watch the 0E down here, it switches to bank 0 because that's Heatman stage. So now we've switched to Heatman stage and we can reference the appropriate blocks. We do a few more things in the bank switch sub and return. So now we're back in level environment collision check sub, and we can proceed with doing heat man specific checks. So we branch ahead to this fine tile offset, and we hit a section of code that was kind of one of the longest things I feel I've had to investigate, because if you look at this without any comments and any labels, in fact, I didn't label much of this, it's really just a whole lot of arithmetic that doesn't really make sense. And you kind of have to move forward through all of it and finally find out what it is that these numbers are influencing, and then work it backward. And all of this code that we're walking through right now is basically getting us to a certain place in the ROM to figure out what the current 32 by 32 pattern is that the front of Mega Man is in. Again, this is all related to getting the appropriate address in order to isolate the 16 by 16 tile that we're currently in. And I've commented some of this code. I feel reasonably sure of what I wrote for each of them. And so by the time we get to this area here, we're interested in which 16 by 16 tile of the pattern we're in right now we need to be examining. I believe the tiles work vertically first, and then you move to the right. So basically, if you find that you're in the right half, you move past, in this case, the top left tile, and then the bottom left tile. And then from there, now we're in the bottom half of the right side. So then we get attributes for that tile. You can even see that I have the Y possibilities here that we just talked about. So we want to pull the tile information out of it, and then finally start examining, hey, what is it? And even then, there are special cases. So you can see that I wrote down earlier, hey, if the offset is equal to B, we're in the Flashman level, and the type is slippery ground, return 5, Metal Man conveyor belt, return 7. So we're not just returning a Boolean value that's like, hey, this is a solid object or not. There are more details that are returned. So we just do a little bit of extra calculations and movement here. And then 0 holds the return value. And we have to switch back to the bank that we were in prior to this call. We know that we came from 0E. That's always true. So we say load E into the accumulator and then do the bank switch. I'm not going to walk it again. Once again, if you watch down here, now we're back in E and we return. So we've returned from our collision checks, and we're basically taking a look at those values and saving them off into RAM. 32, 33, and 34 are used to save the head, body, and feet. We use the same X offset that we used as part of the loop to look up our offset for the Y-axis. So we decrement it and we loop it again. So basically, I'm not going to go into this again, but we loop a second time and a third time, and now we have head, body, and feet. So now with the tile types available for reference in RAM, we loop through them and check and just see, hey, are we running into anything? Did we hit spikes? We start combining the results into address 0. Now, I'm not facing a tile that I'm going to collide with. Head, feet, body, doesn't matter. So basically, it's going to keep ORing a value of 0 and saving it into 0 and combining them. And that's the whole point of this forward check that we're in right now. So we return from the check forward collision sub and hit the was something in front of Mega Man. Nothing was in front of Mega Man. So we skip over that section we talked about with that's used for zipping, and we hit before screen scroll. It's possible that the screen will need to be scrolled, so this handles it. And then after we're done, we hit this final screen scroll left, or a scroll screen left sub will take care of that. Miscellaneous environmental checks, bubbles, ladders, there are a lot of extra things in there. I'm not going to really go over them. I haven't completely reversed the logic inside that subroutine. But that gets us through move Mega Man horizontally sub, and our cycle count is up here. So now it's worth seeing, hey, with Mega Man and 3 blocks on the screen, how many cycles did it take to get through that move Mega Man horizontally sub? And compare it to a percentage of the total cycles available for a given frame. So let's do that. If we subtract the before cycle count from the after cycle count, we get 3,188. At the moment, this number is just trivia. It doesn't really mean much unless you know what percentage of a single frame it is. The number of CPU cycles per frame on average for the NTSC NES is 29,780.5. So if we take our cycle count for the Move Mega Man horizontally subroutine and divide it by the CPU cycles per frame, that percentage is about 10.7%. And the cycle count for the frame is for the entire frame of video, including vertical blank. As an aside for calculations, brace yourselves, here comes the math. This image illustrates a frame of NES video output to a television, and it includes the graphics drawn to the screen, horizontal blanking, vertical blanking, the works. 256 pixels across for NES graphics per scan line, or 341 dots across per scan line when you include the horizontal blanking. The community uses the term dots as their preferred unit of measurement. Not all PPU dots are realized as pixels on the screen. 240 scan lines down for NES graphics. 262 scan lines total when you include vertical blanking. I have additional videos on the channel that break down the 525 line analog video signal and explain 240p if you are interested. Now, how do we get this CPU cycles per frame value? There are 3 PPU dots per CPU cycle, so let's find the total number of PPU dots per frame and divide by 3. I'm leaving out some sub-calculations, but let's keep this simple. So you figure it would be 341 dots per scan line times 262 scan lines equals 89,342 PPU dots total. Divide that number by 3 and get the CPU cycles, and it is 29,780 and 2/3. That number doesn't quite match what I used for our percentage. Why? Without going too deep into it, there is one pre-render scan line between vertical blanking and the next picture, and it can be 1 dot shorter, 340 instead of 341 in every other frame. So, to account for this, the calculation is considered to be 341 dots per scan line times 261 scan lines plus 340.5 dots, an average for that pre-render scan line, equals 89,341.5 PPU dots divided by 3 equals 29,780.5 CPU cycles. That is what I used to find the percentage of execution time for our subroutine. If you wish to separate CPU cycles used while the PPU is outputting an image to the screen and exclude vertical blank due to NMI handling when the CPU tells the PPU what to draw next being there, then I suppose you could say 341 dots times 239 scan lines plus 340.5 equals 81,839.5 PPU dots per frame. Divide that by 3, 27,279.83 repeating CPU cycles per frame, assuming my calculation is correct. Use that to calculate our subroutine execution time as a frame percentage, and you're looking at around 11.69% of total frame execution time when vertical blanking is excluded. Did you get all that? So that's one way to get the cycle counts and figure out what percentage of a frame it takes to execute a given subroutine. Now, another way that's really interesting, I love this feature of the event viewer in Messen, which is what we're looking at right now as the blocks are appearing and disappearing. We've looked at this event viewer before when we've talked about mapper register writes and how we would switch from one bank to another for the MMC1 chip. It takes 5 writes to the register. We've even already talked about it in this video. But this can be used for many other things, and I left the little legend up there on the right side of the event viewer. We can use this thanks to breakpoints in order to see how long it takes to execute code from a visual standpoint for a screen timeline. Because remember, and I'm really glad that I have this crosshair here, so hopefully you can see this. The CPU is outputting a frame of video. In fact, I'm going to freeze this for a moment. The PPU is outputting a frame of video, and it is drawing on the CRT screen from the left to right for a given scan line, and then it goes down to the next line, just like a typewriter. For those of you that know what a typewriter is, wonderful analogy, Chris. And it keeps moving down the screen, left to right, top to bottom. And as it's outputting the graphics on the screen, the CPU is busy doing all the calculations for the next frame. So really what you're looking at is a timeline that has a carriage return, more or less, at the end of every line of graphics. So the start of time for the current frame is here, and the end of time for the current frame is down here. It's technically when you hit line 241. And so basically, this lets us examine duration for execution, and we can do that using a marked breakpoint in the debugger. So let me switch to the debugger and show you how we do that, and you're going to find this fascinating. So here we are in the debugger, and I went ahead and set a breakpoint and let it break right at our Move Mega Man horizontally sub. And you can see the little circles that are out here to the left side next to these ROM addresses. And the reason they're there is because we have breakpoints down here, and they're currently disabled. So I can enable them by checking the boxes on the left here. Now, another thing we can do is use this second column of checkboxes that has an M over it. Kind of mysterious, isn't it? But basically, if I check those boxes, instead of having our breakpoint set, I've turned that off because I unchecked the first column, we have these little blue dots that are up here. So if we return to the event viewer, now I have this area here called marked breakpoints. And if I turn that on, you see all those blue boxes that are dancing across the screen really fast? That's the call and then return from Move Mega Man horizontally. Let me freeze this. So as you can see right here, breakpoint, scan line 27, that's the call to our function. And then down here, this second breakpoint, this marked breakpoint, scan line 55, that's where we've returned. That's the next line right after our JSR. So you can see that the time that it took to execute that Move Mega Man horizontally subroutine is from here to here. So that's how long it took the CPU to do all of that work as the PPU is drawing this frame to the screen. There was a book written about the Atari called Racing the Beam. This applies to more than just the Atari if you want to kind of think about it in a conceptual sort of way. For the current frame being drawn, you have to get all of your work done for the next frame before the current frame has finished being drawn to the screen. And if you can't get it done, then hopefully you've optimized your code in such a way it's designed to handle that. And some games you'll find will, instead of using 60 frames a second, they'll run at 30 frames per second because it lets them double the amount of CPU time that they have to get the job done for the next frame. After the CPU is finished doing all of its calculations for the next frame, it's waiting, hopefully, before we actually get to the NMI. And then during vertical blank, that's when it says, okay, PPU, here are the graphics for the next frame. And you have this much time in order to get all those graphics set so then you can go to the top. And I love the fact that we have this marked breakpoint feature set in the event viewer because it lets us see how long, provided that we know what the code is doing and know where to set our marked breakpoints, we can see how long it takes to perform a certain action. And if I let this roll, again, I can also add the mapper changes. And wow, what a mess that is. But if we freeze this again, I know it's going to be hard to pick out those boxes, but here's the first box right here on scan line 20, and then here's the second one right here on scan line 47. So all of the yellow boxes you see inside that range are the bank switching calls that we have in order to get to the Heatman level, check that level, return, put everything back the way it was. Oh, we have to check the Heatman level again. Oh, return. And hey, I mean, it takes time, right? So you could take that same logic and optimize it in such a way that you don't have as many calls and you would save that amount of time. Now, percentage-wise, no, it's not a large part of a 240 scan line frame to go from here to here on scan line 22. But it takes from here to here to get the bank switch to happen. So if you had a different MMC chip, like one that didn't take as many instructions in order to switch banks, or you optimize your banks or your code in such a way that you don't have to do as many changes, then you would save a lot of time. And so just bank switching alone, for example, if you switched banks less, you would see this end breakpoint from the marked breakpoint would go up higher on the screen because it takes less time to execute that subroutine. And so once again, it is kind of still an instance of racing the beam because you only have so many cycles to get your work done. And the amount of work you have to get done is going to change depending on what is happening on the screen. The last thing I wanted to look at was the performance of Mega Man 3. While I haven't reversed any code for this game, pairing it with the event viewer will allow us to observe how busy the CPU is for a given stretch of gameplay. One of the statements I often see made across the web is that games slow down because it is too much for the NES to handle. While that statement is technically true, it isn't because there's too much on the screen. Have you ever seen or played Rekka? But rather, the code used to handle all of the necessary tasks per frame is not designed in a way that allows it to complete those tasks in an acceptable amount of time. Mega Man 3 had a new programmer enter the picture that was responsible for implementing new features, such as the slide, new enemies, and more. The cartridge tech moved from an MMC1 chip to an MMC3 chip. That means bank switching had to be re-optimized. So you have two challenges: code optimization for all the various checks, such as collision detection and enemy behavior, as well as optimal bank switching during a frame, meaning change banks the fewest number of times required. This stretch of Sparkman's stage is one example of an area where performance seems to slow down. It would appear to be because of these large blocks. Well, that must be it, right? Maybe all the flashing and the large blocks falling is too much. If you're a gamer and not a developer, I get it. Making observations and drawing conclusions based on what you see is only natural. If we take a look at this same area in the event viewer, we can see a decent chunk of bank switching occurring as the frames roll. I don't want to get too far into that right now as we're at the end of this video, but this gives you an idea that a lot more is going on here for each frame than you might think. The slowdown occurs when I jump over the second and third column. Can you see that? I feel like it's pretty noticeable. Now watch this. No slowdown. I am not overclocking or using any read-ahead features of the emulator. This is a patched ROM where the code for Mega Man 3 has been reversed and then optimized in order to perform the same tasks using less code, meaning fewer cycles are required. And I wanted to use the fact this patch exists to show that what you see on the screen isn't too much for the NES to handle, but rather suboptimal code and bank switching, among other things potentially. This isn't a knock on the programmer, as they would have had to create Mega Man 3 using someone else's code with a potentially unreasonable deadline, limited ROM space, and by the way, this patch increased the size of the Mega Man 3 ROM, and dev technology of the time. But I hope this illustrates how much code, ROM layout, bank switching, etc. can influence performance. Hope you enjoyed this one, because we aren't done with Mega Man 2 yet. Thanks for watching, and I'll talk to you again soon.